Okay, class, we're going to deal with the concept that is very useful in terms of chemical bonding called hybridization. So hybridization, that's what's going to go here in this first gap. Hybridization is the theory that atomic orbitals, like the s, p, and the d orbitals that we have in atoms, can combine to give a new set of atomic orbitals that have a better orientation for overlap. When two atoms come together and they form a bond, the s, p, and d atomic orbitals may not overlap very efficiently with each other to give a nice, stable overlap region to form a nice bond. To improve their bonds and make the bonds more energetically stable, they can take their s, p, and d atomic orbitals and they can blend them a little bit to form new orbitals with different shapes that have better overlap. So that's what's going to happen. We're going to take s, p, and d orbitals and we're going to overlap them and we're going to blend them so that they can overlap better with their neighbors. And the blended orbitals are called hybrid orbitals, which is why we call this hybridization. So the new orbitals are said to be hybridized orbitals, and an atom with hybridized orbitals has a hybridization. And the hybridization is based on the number of original atomic orbitals that were used to create the new hybrid or blended orbitals. The hybridization is therefore based on the number of electronic domains around the central atom. So we've talked about how to determine the number of electronic domains. Well, the electronic domains are going to determine the hybridization. And here's how we do it. Every electron domain requires a new hybrid orbital. So if you've got 5 electron domains, that means you had to have 5 hybrid orbitals. Every one of those hybrid orbitals that you formed required an atomic orbital to form it. So for example, an s, 1 or more of the p orbitals, and maybe even 1 or 2 of the d orbitals had to be used as ingredients. So, for example, if an atom has 4 electron domains around it, such as in water, for example, that has 4 electron domains around it, then it must form 4 new hybrid orbitals around it. And therefore, it must have used 4 atomic orbitals to do so. And just to remind ourselves, atomic orbitals can be an s orbital. We can have p orbitals, and we know that there are 3 of the p orbitals in an individual subshell, right? And we can have even 1 or 2 d orbitals if it's one of those atoms that can expand its octet. Okay. Atoms use as many atomic orbitals as they need. And they're going to use them in this order. They're going to use their s orbital first. Then they use as many p orbitals as they need, up to 3 of them. And if they need more orbitals than that, they can even use 1 or 2 d orbitals. For example, if 1 s orbital were used and 3 p orbitals were used, then 4 atomic orbitals were used, and we get 4 brand new hybrid orbitals. And these new hybrid orbitals are named after the atomic orbitals that were used to make them. So the 4 new hybrid orbitals would be called sp3. So it's a lowercase s, it's a lowercase p, and then a superscript number to tell us how many p orbitals were used. And in this case, we used 3. So we would have 4 brand new orbitals, and each orbital would be called an sp3 orbital. And the central atom, for example, the oxygen in a water molecule, would be said to be sp3 hybridized. Okay, so just to reiterate, we have atomic orbitals. The atomic orbitals are s, up to 3 of the p orbitals, and maybe even 1 or 2 d orbitals. So notice how many that gives us. It gives us 1, 2, 3, 4, 5, 6 that can be used to make up to 6 hybrid orbitals, and therefore we can have up to 6 electron domains, up to an octahedral electron geometry. So we're going to go through this table here below just to fill in the table and make sure that we're tracking all this. So if I have 2 electron domains around an atom, then I must form 2 hybrid orbitals for bonding. If I form 2 hybrid orbitals for bonding, then I must have used that number of atomic orbitals to do it. So if I use 2 atomic orbitals, then I would have needed an s orbital and a p orbital. So an s and a p orbital, and that would have given me 2 orbitals, and each of the orbitals would be named sp. So sp would be the hybridization of the atom. sp hybridization. Okay. 3 electron domains requires 3 hybrid orbitals. 3 hybrid orbitals required 3 atomic orbitals as ingredients. Which atomic orbitals were used? For 3 of them, I needed an s and then 2 of the p orbitals. So I would have had an s and 2 of the p orbitals, and that would have given me 3 orbitals, and the name of the orbitals and also the hybridization of the atom would be sp2, because I'm using 2 of the p orbitals. Okay. If I needed more than 4, if I needed 5, I could use a d orbital. If I had 6, I could have 2 of the d orbitals. So go ahead and see if you can fill in the rest of this chart. Pause the video, and when you're done, continue the video and I'll show you the answers. Okay, coming back from pausing the video, filling in the rest of this chart. 4 electron domains means we had to have 4 hybrid orbitals. 4 hybrid orbitals for bonding needed 4 atomic orbitals as ingredients. So we would have had an s, a p, and a p orbital, and that would have given me 4 new hybridized orbitals, and the name of those hybridized orbitals, which is also called the hybridization of the atom, is sp3. That's what we did up here. Next, we've got 5 domains around an atom. That means we had 5 hybrid orbitals that had to be created for bonding. That means we had to use 5 atomic orbitals as ingredients. So we'd have used an s, 3 of the p's, and 1 of the d's. And that gives us 5 new hybrid orbitals. And the hybrid orbitals are each called, and the hybridization is called sp3d. An S, 3 P's, and a D gives us the 5. And the same for 6. 6 electron domains, 6 hybrid orbitals, means 6 atomic orbitals as ingredients. And there we go. sp3d2 hybridized. So the hybridization is really just a simple matter of figuring out how many electron domains you have, and then that's how many orbitals you need. 2 electron domains, there's one, there's another. 4 electron domains, there's one, and there's 3 more. 6 electron domains, there's one, there's 3 more, and there's 2 more. And that's all you need to do. This exercise is asking us to assign the hybridizations in the acetate ion. Now, I would not expect you to know how to draw the Lewis structure for the acetate ion. It's a more complex Lewis structure than you've been taught because it has more than one central atom. However, I thought this would be a good example to use because it gives us a lot of different opportunities to practice assigning hybridizations. When it says assign the hybridizations, we need a hybridization for every atom in the species. So I'm just going to draw an arrow to it, and then I'm going to write whatever hybridization is appropriate. Okay? So first of all, I'm going to deal with these hydrogens. Now, hydrogens, they only have one electron domain around them, right? Well, if you only have one electron domain for bonding, there are no hybridizations. There is no blending because you only had one atomic orbital. Remember, hydrogen has no p orbitals because its valence shell is n equals 1, and there are no p orbitals in the n equals 1 valence level. So hydrogen does not hybridize. It has simply used its s orbital to overlap with carbon for the bond. So there's no hybridization for hydrogen. Here again, there's no hybridization for hydrogen, no hybridization for hydrogen. These are just s orbitals that they're using. But now we get to a carbon here, and carbon does hybridize. We can see that it has more than one electron domain around it. It has 1, 2, 3, 4. 4 electron domains required 4 hybrid orbitals to be formed, 1 for each of these bonds. To make each of these hybrid orbitals, it had to use an atomic orbital, and therefore there are 4 atomic orbitals that it used. So each of these bonds is created by overlapping a hybridized orbital called an sp3 orbital. So that carbon is said to be sp3 hybridized. Let's take a look at this carbon. How many electron domains? 1, 2, 3. So I had to have an s and 2 p orbitals. 1, 2, 3. What about this oxygen? How many electron domains? 1, 2, 3, 4. It must be sp3, hybridized. What about this oxygen? How many electron domains? 1, 2, 3. It must have used an s and 2 of the p orbitals. So here I have assigned the hybridizations in the acetate ion. Again, hydrogen is not technically a hybridization. It simply uses its s orbital to overlap to form its bond. But I went ahead and included that to show that hydrogen is using just an s orbital. Okay, we're going to move on